All right, last but definitely not least is springs, the always forgotten type of force. Spring forces. So we got Hooke's law that says that if you have a Hooke's law spring, an ideal spring, that the force the spring exerts will be dependent upon the displacement of that free end of the spring. So if you just pull on one end of a spring and the other end is not fixed someplace, you'll just drag the whole spring on the table like you would a book. So one end of the spring would need to be fixed or secured somehow so that the spring is required to stretch. The spring, stretching, string, anyways, lots of hard words to say. So when a spring is attached at one end and the other end is free, it's got some equilibrium position where the free end that's not secured to an immovable object wants to hang out. At that point, you would say there's no spring force, or there's no net spring force. It's in equilibrium at that point. If you attach some mass to the spring, then you can pull on it, release it, and it'll bounce back and forth, and it'll cause that mass to accelerate. What we want to do is just figure out what the force is in a static problem, not where there is any sort of motion actually happening. So in this case, something at the equilibrium position, the force should be 0. If we stretch the spring out, we displace it, this delta x in the positive x direction, then the spring force, F sub s, should try to direct it back. We call it a restoring force. It wants to restore the object to its low energy position, back to equilibrium. At this point, it's the end of the spring is in a place it doesn't want to be. That means it's got potential energy, and it wants to convert that potential into kinetic. It wants to get rid of that potential energy. Now, if we do the opposite, if we were to compress the spring, if it's a compressible spring, we give it a negative displacement, a negative delta x here, then the spring force is again going to push opposite of our displacement. So we say that Hooke's law, or the ideal spring law, is spring force as a vector is equal to negative k times the delta x as a vector for its displacement. K is just some constant. We call it the spring constant. I'll scroll down here. Its units are newtons per meter, because for every meter of displacement that you give, you should get some newtons of force. So K is newtons per meter. Generally speaking, we'll just calculate the magnitude of the spring force and use that, so you can drop the vector for x and just have a displacement x as a value, or position relative to 0. And the spring force, we drop any positives or negatives from it as well. It's just the amount of force. And then we can always put this into a dynamics equation, and we can figure out whether it's positive or negative depending upon the direction that the force is acting. Let's try that. So here I've got a problem, or I should say we have a problem. A 2 kilogram box rests on a frictionless incline as shown. The spring is stretched 0.15 meters from its equilibrium position. So if there is no mass attached, it would hang out someplace. But because there is a mass attached to it, it's hanging out a little bit further away from that location. So maybe the equilibrium position is right here. And it's stretched out a little bit. The free end of the spring is not at the equilibrium position. So we want to draw a free body diagram for the forces acting on the mass, m, and then calculate the spring constant. It says that the incline is at 20 degrees. So let's start by drawing a free body diagram. Just like anything else that's on an incline, we have to take into account the fact that we have an x and a y axis that's a little different than normal. If we draw the x and y axis like so, that means the only force acting on this object that is not in line with the x and y axis would be the force of gravity, which would be acting straight down towards the Earth. And then we can find its components in order to solve the problem. So for a free body diagram, and also I'd like to point out here, it does say it's a frictionless surface, so we don't have to worry about any sort of force of friction and which way it's going. The object is at rest, so that means there could be static friction, but let's just assume gravity and the spring are taking care of all the dynamics here. So free body diagram, we would have the force mg going straight down. We would have the spring force trying to pull up towards the equilibrium position. That'd be Fs. And then we would have the normal force. And again, let me go ahead and add in a dotted line like we normally would if you have an incline to represent where the incline is. And we'd have a normal force acting perpendicular to that incline, supporting the object, preventing it from sinking in. So there's a free body diagram. Now we need to write some net force equations in the x and in the y direction. So that means that this one force that is at an angle other than 90 degrees or 0 degrees from an axis, we got to break it into components. And we fall back on our good old-fashioned mnemonic device. It says when we split the weight force into components, there's a crushing component that is the cosine of theta, and we have the sliding component that is the sine of theta. So we got those two components, mg cosine theta, which again we do not draw in the free body diagram. We only draw the actual forces in their real directions. It's in the dynamics equations that we include cosines and sines and whatnot. That's going the y direction, which is lining up with the normal force. And then in the x direction, we've got the mg sine theta. It's trying to slide that block downhill, but the spring force is trying to pull it back up, trying to get the end of the spring back to its equilibrium. So if I draw some equations over here, I would say draw equations. How would I say write the equations? In the x direction, we can call it sigma fx. Going uphill, we can call it positive, so I would have spring force. And going downhill, I would have mg sine theta. And those would be equal to normally m times a, but in this case it says it's motionless. It's being held still. Well, it doesn't say motionless, it says at rest. So it's just sitting there. So there's no acceleration at this time. It's being held there between those two forces. And then in the y direction, although we don't need it for this problem, we might as well write it out just to be thorough. We'd have normal force in the positive y direction, and then mg cosine theta, crushing component, subtracted from it because it's pushing into the negative y direction according to my little purple scale here, and that again is also equal to 0. Now we're trying to figure out what the spring constant is, so we have a third formula we need to write in here, and that third formula is that the magnitude of the spring force is equal to k times x. So we can substitute that into the x equation and see what we get. Let's you can take a pause here, you pause the video, calculate it up, and then see what you get what I get. In fact, I'll pause it and then just do a big reveal. That sounds like fun. Here we go. Boom, there we go. Here's my answer. So I've got spring force minus mg sine theta equals 0 from up above. I replaced I went ahead and added mg sine theta to the other side, replaced spring force with k times x. Then I solve for k, take mg sine theta over x, plug the numbers, I get 44.7. Now I kind of ran out of space to write the units there, but that's 44.7 newtons per meter of stretch. So at 0.15 meters of stretch, we're not going to get 44.7. We're just going to get enough force to prevent that sliding component of weight from accelerating the object downhill. It's being held at rest because those two forces are in equilibrium with each other. Now, if we wanted to, we could call this a new equilibrium position for the spring and add more stuff on and recalculate, but we're not going to do that. So let's go ahead and do a challenge problem next. The challenge problem, well, it's challenging. What if we included what we did in review 3, circular motion, with what we're just looking at here, spring forces. So if something's going around in a circle, it needs a force to provide that centripetal force. That centripetal acceleration is produced by centripetal force. It's the net force acting on it towards the center of a circle. Well, if it's going in a circle, what if we replace a string with a spring? We add the P instead of the T. Then we have to say that the spring force is going to provide that centripetal force. So let's say I've got a 1 kilogram mass swinging around on a horizontal circular path, so we don't have to worry about gravity acting on it at any point. Let's say it's frictionless surface that it's on as well. Has a speed of 5 meters per second at this exact moment. The mass that's attached to the end of the ideal spring has K is equal to 416 newtons per meter, and that has an equilibrium length of 0.5 meters. So we know it's a 1 kilogram mass. It should have an equilibrium length of 0.5 meters. By what length will the spring stretch as the mass moves at that constant 5 meters per second? Now, this is a bit tricky. I want you to maybe pause this for a second and kind of consider, how are you going to include everything? What are you going to do to figure this out? This is a hard one. Now, it would make sense, hopefully, that if this thing were going faster and faster and faster, that it would require a greater centripetal force. But the only way you can get a greater centripetal force is by stretching the spring out. And by stretching the spring out, you're increasing the radius, so centripetal force might go down. So there's a fine balance here. If you just move something out farther, it requires less force than if it was in further, but by pulling out farther, you get more force. So there's an equilibrium, there's a balance here between all of these in terms of force required and force provided. So I am going to say that there's some equilibrium position here. You draw a dotted line on the spring and say that this is the equilibrium position. But I need a radius r. And that radius r is going to be made up of that equilibrium length, which they tell us in the problem, or I told it because I wrote it, is 0.5 meters. And then the rest of that radius is going to be the x, the amount of stretch. So we have to put that into our formula. In this case, if we want to think of it in terms of spring force trying to pull towards the center of the circle, and that's providing the centripetal force, we can say spring force minus nothing, nothing's going away from the center of the circle, has to equal centripetal force. And then we can substitute in things, and in this case it would be x for the spring force, k times x, and for the centripetal force it would be mv squared over r. So far so good. Those two forces must be equal to each other. I need a certain centripetal force that's being provided by the spring. I could have put tension, I could have put gravity, I could have put anything here, but in this case it's the spring that's doing it. But here's where it gets tricky. I know K, I know M, I know V, I don't know R, and I don't know X. So that's where I have to substitute in, say let R equal 0.5 plus X. Now I've got a little algebra problem that I can set up here. This is how far I've stretched the spring. This is the original length plus the stretch. So I have Kx is equal to mv squared over the quantity 0.5 plus x. And from here, I can go ahead and go about some solutions. I can multiply this over, and do all the stuff. Now, in this case, you are going to end up with something that's a little bit ugly to solve, but the setup is half the battle, right? We want to be able to see what's going on. So real quick, if this x value were 0, you'd have no spring force. And if the x value was 0, this side would have to be 0. So the only way you could get 0 here is if there's no velocity. Because if x is 0 on the denominator, you still have a radius, 0.5. But in order to have no force on the spring, you have to have no centripetal force required, which means no velocity. And as this velocity increases and increases, you square it, it gets really, really big, you would need to provide a larger stretch. But it's not a one-to-one. There's always that extra little 0.5 there. So the original length of the spring is going to help us, it's going to allow us to have a solution. Because if it was just an x down here, well, then it'd be a kind of a weird problem. As the velocity increased, the spring stretch would just increase at the same sort of rate, and that's just not the way it's going to work. So how about you try to solve this out algebraically, see what you get. I'm going to go ahead and pause it, pull up my solution, and we'll compare. Now, just as a little teaser, you should end up with a quadratic that looks something like this. And from here, you gotta plug in the numbers. We know the K value, we know what mass is, we know what velocity is, so we can put this in probably into a calculator and get a solution. So do it. And you should get about 0.1 meters. Seems like too simple of a solution. Not exactly 0.1, of course, but you can always go back and then check that by putting in 416 times 0.1, and you get 41.6, and you put in 5 squared times 1 over 0.6, and you get 41.666. It's close. So there's a little bit that being off, but 0.1 meters is the stretch of the spring. So that's a little tricky one, but hopefully that helps you get a better sense of connecting some of the other forces and the ways we solve things, circular motion, setting up dynamics equations, etc., in order to get a solution for a hard problem. Anyways, thanks for watching.